Topic line 2, regression with time series data, stationary variable. So we have studied a simple linear regression model. Y is alpha plus beta xi plus ei. I runs from 1 to n. We have n observations. Now we have our data are time series. So in these cases, we change the subscript from I to t to denote that is time. And time goes from period 1 until period 2 until period t. So we have t observations. And in analyzing time series data, we are typically interested to model a dynamic relationship. So what do we mean by dynamic? Dynamic means current values of variables are correlated with their past values. Firstly. Secondly, they are correlated with they can be correlated with both the current and past values of other variables. Okay, that's what I mean by dynamic. So we have past values of these y and x affecting y. So how can we incorporate dynamics into our regression model like this? There are different ways resulting in different models, and we will study some. For example, like finite distributed lag models of order q. So now xt affect yt is lag, is 1 period lag, 2 period lag, until q periods lag, affecting current value of y. So we call this model finite because it only lasts for q periods, and it's a distributed lag. The impact of x on y is distributed over current period, 1 year lag, 1 period lag, 2 period lag, and q period lag. So that's what why it is called finite distributed lag models. We could have AR models. We already studied it previously. So y does not depend on x now, but it depends on its own lag. So that's why it's called autoregressive up to period p. So autoregressive model of order p. We can have both. Then we get autoregressive distributed lag models, ARDL PQ. P is the order of the autoregressive component, and Q is the order of finite distributed lag component. So we have yt is delta plus theta 1 until theta p. That's the autoregressive component, plus theta 0 plus xt x delta plus delta 1 times xt minus 1, so on and so forth, until delta q times xt minus q. So this is the distributed lag models component, and this is the error terms. We can even have infinite distributed lag models. So now yt depends on x, the contemporaneous x, 1 period lag, 2, so on and so forth, until far into the future and into the past. And in such cases, it is necessary that beta s will decrease. The further into the future, it becomes smaller and smaller. Okay. The dynamic can occur in the error terms as well. For example, we can have an autoregressive error models. Yt is equal to alpha plus beta 0 times xt plus et error terms. Et follows in AR1 process. Et is in AR1 process is equal to rho times et minus 1 plus nu t, where nu t is IID normal, let's say. Okay, let's look at the autoregressive distributed lag models. It's of these forms ARDL, PQ. And so we have data Y, data X. We can actually, under appropriate assumptions, we can estimate this model. We can use this model for either for forecasting, like we use AR2 or AR1 models for forecasting, or we can use it for policy analysis. So now for the policy analysis, we will be interested to the individual coefficients of this, for example, theta 1 until theta p, delta 1 until delta q, delta 0. So we want to have a causal interpretation of this. So we need assumption that at least the assumption that the error terms is exogenous. Okay. Right. So recall our assumption of MR1 to MR5 within the time series framework. So two assumptions among these 5 assumptions are quite restricted. First, strict exogeneity. So it says in our time series context, it says that expected value of ET conditional on X. X here, X is X1, X2 until XT, the whole right-hand side variables. And this XI, XT, each XT consists of YT minus 1 until YT minus P and XT. Okay, this XT should be like bold XT. XT minus 1 until XT minus Q. Okay, so by writing by conditional whole X is actually a very strong exogeneity, very strict exogeneity, and this might not hold in the time series framework because here we have time series data. Typically, they are correlated across times. The error terms can be correlated with the error term of this period might depend on previous periods y, negative y, for example. The second assumption that is likely to fail is no serial correlation or no autocorrelations. Covariance of ET and EX conditional again the X, the whole right-hand side variables is equal to 0 when t is not the same as S. Okay, we can actually relax these two assumptions a little bit. So rather than requiring the strict exogeneity, we can relax it to contemporaneous exogeneity. That means now we are conditioned on JT, not the whole J. Okay, J will be J1 until J big T. Okay, but JT. So condition on the current period G, which G contains all right-hand side variables, all this until this, and this, and this. That could include both negative X and negative Y. So that's exogeneity conditions. No serial correlations. Now again, we will not condition the whole G. Rather, instead we require to condition on JT and JS. The covariance of ET and ES is equal to 0. Still, this may be strong. We still in the particular context of application, we still need to query, check whether this is holds or not, is realistic or not. So, okay, for simplicity, let us work with models with only one X and is lax, or let's look at finite distributed lag models. So yt is alpha plus beta 0 times xt plus beta 1 times xt minus 1, so on and so forth until q plus error terms. So this is a finite distributed lag models. It's finite because the impact of x on y disappeared, vanished after q lags, q periods. Okay, and it's distributed because the impact of x is distributed across xt minus 1, xt minus 2 until xt minus q. Okay. So for the coefficient of beta s for this beta, to represent causal effect, we need ET to be uncorrelated with both the current and all past values of x. So we need this. Condition on xt, xt minus 1, xt minus t, so on and so forth. The conditional expectation of ET is equal to 0. Given this, we can derive this, okay, because of yt, we can plug this one into here. And a little bit algebra, we can get this. And this is equal to expected value of yt conditional this. Okay, rather than condition on the whole past history, we are conditioning to the history up to t minus q. That's sufficient. Okay. So given this assumption, the lag coefficient beta s can be interpreted as the change in expected value of yt when xt minus 1, when xt minus s changes by 1 unit, while x is held constant in all the other periods. So in terms of partial derivative, is this way. Partial derivative of expected value of yt conditional xt with respect to xt minus x is equal to beta s. So in this case, beta s captures the causalities from x to y. Right, we need a few assumptions for finite distributed lag model for us to estimate this model properly, for us to achieve, for us to be able to use it for policy analysis. First one, the time series y and x are stationary and weakly dependent. Okay, they have equal mean variance across time. Mean variance does not depends on times. The correlation disappears as times become further apart. Assumption 2, the FDL model describes how y responds to current and past values of x. Basically, this says that the model is correctly alpha plus beta 0 xt plus beta 1 xt minus 1 plus beta q xt minus q plus error term. This model is correctly specified. Assumption 3, the error terms exogenous with respect to the current and all past values of x. So that's the exogeneity conditions of error terms. Assumption 4, the error term is not autocorrelated. Okay, this might fail. So we will discuss what we can do if this fails. And assumption 5, the error term is homoscedastic. The variance. Okay, this is sigma squared. Okay, sigma squared is constant across time. Again, this can fail as well. Okay, under these assumptions, OLS estimation is valid. The coefficient estimates are consistent. Standard errors are correct. Hypothesis testing interval estimates are valid. So assumption for FDL5 might fail. In time series models, errors are highly likely to be autocorrelated. They correlate across time. Also, heteroscedasticity is also possible. So how can we deal with it? The easiest way or widely used in application context is to apply heteroscedasticity and autocorrelation consistent. Estimate of the standard error, which is also known as Newton-West standard errors. Okay, when we estimate the model, the finite distributed lag model or auto ARDL models, we can predict residuals and check the correlogram of least square residuals to see whether there's evidence of autocorrelations of error in the error terms or not. So visualize this using correlograms. We can also conduct Lagrangian multiplier tests. So now hypothesis. So now basically error term we're testing rho 1 et minus 1 plus rho 2 et minus 2 plus and here rho q, okay, et minus q plus nu t. Okay, estimate this equation, but error term we don't observe, but luckily we can predict, we can estimate them. So we do this and run the regression, estimate, conduct a joint hypothesis test using the test statistic is t times r square of this auxiliary regression. R square comes from these auxiliary regressions, and it has a chi-square distribution with m degree of freedom. Okay, this. So we can do this Lagrangian multiplier test. We can also use a very classical Durbin-Watson test. The null hypothesis is no serial correlation. So if the computed DW statistics is around 2, then it is compatible with the null.